try to find it first.
So you're doing
Is there something that captures that debate and dialogue? I thought they were talking about so.
All right. So we've selected our events, and now's the time to see if we can extract some event density matrix elements from our nice, simple Monte Carlo data set. And Mike's going to show us how to do that. Mike.
Okay, so here we are. We finally figured out how to extract our signal. But we pretty much looked at dealing with the Sim1 data where we just use Pythia as sort of a catch-all to just throw a little bit of everything. I'll talk about how you throw something with a little bit more physics using amp tools. So the first thing is that if you're using the iFarm, a lot of these examples are gonna require some little small files to be made, so you won't be able to just compile things into your own directory. So if you can just copy the full session folder over into your hall DMI and then go into it. Is there anyone who is using iFarm? It's just Tegan? All right, so Tegan, if you can do that, that'd be great.
Just kind of loose.
Okay, so basically what I'll talk about is kind of twofold. So the name of the session is Fitting Spin Density Matrix Elements, but really I'd say we're going to spend most of our time generating the data that we'll use for the fit. In reality, we're not going to generate all the data. We're only going to generate 25 events, but we've already generated 1 million events for you to use in the fit. So basically, hopefully at the end of the session, you'll understand how you throw events, how you use the simulation tools to get through and get something that looks like our data, and then we'll go into using the things that we've already talked about and actually use the monitoring histograms plugin to see all of those things, then use the Omega skimming program to get things from gen into root, and then using the deselector to go from root into more root where we have made all of our final cuts, and then I'll talk about getting that into a format for amp tools. And then once we've gone through all this simulation work, then we can see how we actually do the fit in amp tools. So in order to do the analysis with amp tools, you need 3 files. So the first one is a file that has the correct physics signal after all your event selection has been performed. So after all these cuts, we throw 1 million events and we send it through the whole chain down until we've gone through all the event selection. The other thing is that we need a file that doesn't have the physics that we're interested in, just something kind of thrown flat in the angles. And then the third one is the result of that file going through all of your analysis cuts. Because what we're going to want to do is correct for the acceptance of all of your cuts and the geometric acceptances of the detector, and trying to then use that to get out the physics signals that we put in, hopefully. Okay, so I stole these slides from Ryan Mitchell, who gave this presentation a long time ago, but it gives sort of the idea of what amp tools is. It's amp tools doesn't really provide any of the physics. That's up to the user, is left to provide all of this. But since we've been using this within GlueX for some time, there's already some pre-existing code, and we'll go into that a little bit later. So basically, it's just a set of C++ classes for amplitude analysis. So what the user needs to provide is some kind of data reader to read the data in, and that's already been made for us at GlueX. And a data writer that you can then take the things that come from, if you're using it for simulation, you can write it out in a format that's appropriate for your experiment or for the next set of tools. The amplitudes themselves, that's where the physics comes in, and that's something that the user needs to describe and code up themselves. And then I'm not going to use the plot generator, but there's additional tools to then investigate sort of the quality of the fits that come out of this using their own set of plot generators. So basically, like I said, the user is just all about writing the amplitudes and some of the other just helping functions in between. So basically, this is sort of how amp tools is designing the problem for you to solve. So you're basically going to try to expand the intensity in terms of these amplitudes. For us, we're just going to have one amplitude that has to do with that has to do with the spin density matrix because of the way that we're going to have this toy model work, and I'll describe that a little bit later. But in general, you would have something like this, where you have these decay amplitudes that each of them has their own complex term that multiplies them. These are all in a coherent sum that you then square. There's some incoherent piece that's available too if you want that. And in the end, you get some intensity as some function of the kinematics. So what's nice about amp tools is that this is formulated in a way that sort of comes up very often in these problems where you have this intensity, but it then gets weighted by the experimental acceptance, and that's what you actually measure, is how many you see in this particular kinematics. So this is sort of built in at the ground level where you have this acceptance correction coming in what you have. Now what goes on in the fit is basically an unbin maximum likelihood fit, where you basically go event by event and basically calculate what the likelihood is, and then vary this in order to minimize the negative log likelihood. So really the code's been designed in a way that's ideal for parallelization and use on GPUs. I haven't spent the time to make this particular code optimized for any of that, but that's sort of a thing for the future, is that you can think about when you start to get more complicated problems, you really want to have this parallelized so that it doesn't take years to run. Okay, that's all I'm going to talk about amp tools. I'm really not the expert on the package itself. If you have real questions, you can ask Matt or look at some other things. The link to this example itself is up in the upper right. There might be some updates since then about exactly what's in the software. But. Okay, so I am going to talk about this toy model. This is basically how we're going to be modeling the system. And I want the theorists to look away because no one likes seeing that three-body decay there, and it's just not a very physical model here. But basically, we're looking at the intensity as just some normalization that we're actually not going to calculate ourselves. And then some phase space factor that gets multiplied by a Breit-Wigner, and to describe the omega sort of propagation. What we're really interested in is this W term that describes the angular distribution of the omega decay. And then just some t dependence that basically sets the scales there. Okay, so Curtis started talking a bit about this, and so I'll present it in I guess this is just the same way, but so basically what we have is we have this term that describes the angular distribution as some function of the spin density matrix elements that are there, and these three angles. Capital phi, lowercase phi, and theta. So capital phi is the angle between the production plane and the photon polarization plane. So if you have, say, an incoming photon that has parallelization parallel to the floor, and you have some production plane there, that angle between the two is that big phi. And then theta and small phi are the angles relative to the chosen quantization axis. So here is where you kind of have your own choice, but depending on the physics that you're trying to look at, you'll choose one or another one. So for us, we're going to use the helicity frame, where the z-axis is in the direction of the outgoing recoil proton in the overall center of mass frame. And this is good in the cases where you have S-channel helicity conservation and natural parity exchange, like Homeron exchange. Because in that case, if that's really all you have there, most of those spin density matrix elements turn out to be zero in that frame, and you really only have two that are non-zero, if that's all that's going on. So there's other frames that are useful for other things. The Gottfried-Jackson frame, where the z-axis is in the direction of the photon in the omega rest frame, that's more useful for if you have a case where you have pion exchange. There's other frames that you can use as well. The y-axis is the normal to the production plane, and then the x is just gotten from the other two. So, like I said, we'll use the helicity frame here. And if you're looking for more details of the derivation, you see Curtis's talk, but the sort of formulary paper is there from Schilling.
It's an Adair frame? That's one?
Yeah, the Adair frame. It's the same as the Gottfried-Jackson frame, but here the z-axis, it's in the overall center of mass frame instead of in the omega's rest frame. So you basically just pick, it's either the I'm not sure exactly what it's useful for or what the case is that you would use that for, but I know in Mike Williams' analysis he did everything in the Adair frame, but it's sort of at lower energy where you have more contributions that aren't just Pomeron exchange. Okay, so now I'll do the thing that everyone hates, and I'm going to bring up some code, and we're going to look at it. So this slide, when you have this on your own, you can go sort of in each of these, and this is the main code that's driving it. So I've described to you sort of what the way we're going to model the reaction, and basically we're going to use this generator called Gen omega 3 pi. That's at this link. And within that Gen omega 3 pi, that's sort of the code that's driving things, and it uses the AMP tools framework. And then within there, we're going to have to describe each of those terms that I was talking about. So there's a phase space factor, the angular distribution I was talking about. The t dependence is actually built in with the generation of the Dalitz decay, and then just some Breit-Wigner that I was talking about. So the benefit of this with AMP tools is that some of these things, once you generate them, you can reuse them for your own code. And there's already examples that are in this AMP tools amps and AMP tools MC-Gen libraries within SimRecon. And there you can see examples of how this has been used in the past and different things to do there. So I'll just take a quick tour through some of this. All right. Like I said, the thing no one likes, but it's useful once. Okay, so C++ code. So basically, what you're going to have is just this executable sim omega 3 pi, where basically you're going to set some mass range. You want to model the intensity of the different photon energies appropriately. So we'll make pretty extensive use of this coherent Bremsstrahlung generator that Richard Jones wrote. So we'll use that in order to model the shape of the photon intensities and also the polarization of each of the photons. So we're going to want to have a per energy polarization value since our polarization is not constant over the different photon energies. To be honest, this code is pretty much just it's sort of not that important because it's none of the physics embodied here, but it's just sort of how you register the amplitudes. This is where it generates the kind of input 4 vectors for the rest of the weighting. I'm not going to talk too much about this one. This one you can just sort of step through and see how the actual selection from it is going. Where things get more interesting or what we've talked about basically is the angular distributions. So in the angular distributions, we're going to use, so this is just the wrapper for Richard's routines. But when you set these AMP tools amplitudes, you basically have, when you see the configuration file later, we're going to call the name of the class and then have a string of just values that comes after it. And all these AMP tools amplitudes, it basically will go through that string and parse it into pieces, and then each of those will pass as arguments into your constructor. So we will have, 9 different spin density matrix elements that will pass into this 3 pi angle Schilling function. By declaring them as AMP parameters and registering the parameters will allow us to use them in a fit later. So basically here is where we start to use the coherent Bremsstrahlung code. So we define the range over which we want the coherent Bremsstrahlung to be produced, whether we want to have the polarized piece or if we just want a sum of incoherent and coherent. And basically we'll just fill one histogram with the total flux, the polarized flux, and that will allow us to get out what the fraction of polarization is for some given energy. So at the end of this, you can look at the code later if you want to, but you just get out this, we're storing it in a root histogram. It's not necessary to do that, but that's just convenient. And so now this pol frac versus E will contain the polarization fraction as a function of the energy. So what happens on the event by event basis is that you calculate the amplitude. So every one of these amp tools amps has this calc amplitude function that basically you pass in the kinematics, and then it returns some complex number. So basically here you see that we have the things that define our reaction. So there's the beam energy, or the beam 4 vector, the recoil proton, the pi plus, the pi minus, and the pi zero. We do all of the work to get into the correct frames and get out the angles that I talked about earlier. So here, basically, we say that, okay, for this given energy, I want to know how much polarization do I have for a photon in that energy bin. And you get that here. And then we basically just calculate that W function that I talked about earlier for that given P gamma, and then all of the angles that we got from the input 4 vectors. So this is the thing that's really going to drive the distribution. This is for later. Okay, so now we.
Photon information in that, or where is it?
So when we throw the photons, we throw them with the correct shape. So we have the right number of photons in each bin. And then in that code, it's taking, okay, so you have one of that energy, what's the polarization of that, of a photon that's in that bin? So are 40% of those linearly polarized, or is it 30 or 20 or 0 at some other point?
So the main thing that goes into that formula is the polarization.
The polarization, so the angles from that particular set of kinematics that was generated.
That's all the time. I'm thinking about the photon itself.
Yeah. So you really just have, so all that goes into that is just that. You just care about the energy of the incoming photon. Okay, so what did we generate this with? So there are some parameters in this model, so what did we choose? So there's this sort of the only energy, or sort of the only measurement with polarized photons at this sort of 9 GeV energy comes from Ballum and others. So basically, there's they measured the rho, omega, and phi at 3 different energies. So 2.8, 4.7, and 9.3 GeV. Basically, you can tell it's a very old measurement because the number of pictures is something they talk about. So it's a bubble chamber experiment, and they use backscattered Compton photons. So the linear polarization that they get there is actually very high. So at the low energies, they see 93% polarization. And up at our energies, it's actually 77% polarized, where GlueX sort of in the highest part of the coherent peak, where maybe 40%, maybe slightly better, but that's all we will see. Okay, so we can look at what their data looks like. It's sort of sparse. So this is the missing mass squared of the pi plus, pi minus, pi zero system. And they're sort of monochromatic photons, so you don't really need to worry about a big energy spread there. So basically, the missing mass squared is here. They cut around this, and this is their distribution for the omega system. So you can see that they only have 1,100 events, which we have that in probably 10 minutes. So basically, what do they fit? So they take these events, they cut around the omega mass, and then they produce plots like this. So what we're basically interested in is this 9.3 GeV. This is their distribution in cosine theta. And then in this psi angle, that's the difference. It's kind of the difference between the big phi I was talking about before and the little phi. So you can see there is some modulation here in phi. This is all in the helicity frame, and then this sort of cosine squared behavior that's sort of indicative of just it being a vector meson. So now let's look at what their results are from their fit. So they fit the t distribution here for 9 GeV. So we had that just basically exponential term, so we're exponentially falling in t. They measured 7.5 inverse squared GeV. And so then if you look at their spin density matrix elements, most of them are 0. The errors are very large. But the two that we will model to be non-zero and that would be consistent with S-channel equalicity conservation are these rho 1, 1 minus 1, and the imaginary part of rho 2, 1 minus 1. So the parameters that we'll use are this t-slope. We'll set this to be 0.4, and then the other one to be negative 0.2. And the rest of them we're just going to leave as 0. Okay. I tend to talk very quickly, so are there any questions before we actually start generating things? Yeah.
Why are we picking those two just as an example?
Just as an example. I mean, if as one of the exercises, I'd say you should pick whatever you want. The difficulty is that, okay, so you pick them, now you have to generate a lot of events, which takes a lot of time to then go through with the whole thing. But for our case, I just picked these since they were the ones that were the most significantly non-zero. Maybe not true based on the errors in that one. But I chose these ones, so that's what we're going to do. Okay, so now we'll get into the interactive part of the session. So if you're in that session 5A directory, there's this configuration file that basically describes how AmpTools is going to generate this data. So as for why we need the fit thing, I don't know why fit is the required thing in here, but it complains if you don't put this. Either way, the reaction, it might just be a warning, but I got rid of the warning. So the reaction is basically, I'm going to name it pi plus, pi minus, pi 0, and these are sort of each of the kinematics that I'm going to define for the gamma p, the gamma, the recoil proton, the pi plus, the pi minus, and the pi 0.
Use the label output files.
Okay.
That's you don't have an output. Good parameters.
Okay. All right. So basically, everything that you define. So this is going to be just some sum of these x-polarized amplitudes. You can look at the details in the last one of these meetings. There was a kind of a more sophisticated amplitude analysis, and if you wanted to see something where you can have the different polarized amplitudes and really see the power of AmpTools for doing real amplitude analysis, I'd suggest you go back and look at the last session. But what we get is, so we can define these amplitudes to be part of this reaction, and basically we're going to use these amplitudes that we had written, that we had coded up before. And you can see, like I was saying, that you have the name of the class, and then you have the arguments to the constructor. So the two that we said were non-zero are out there, and so basically now you have that set up, and then you have this bright Wigner that will describe the line shape. So you have the mass, the width, and then which of these are going to be the daughter particles of this resonance. So then you initialize it, and now that's all you really need in the configuration file. So, okay, the first thing to do is to generate the events. So the generation is pretty fast because all you're doing is throwing the 4 vectors according to these. So let's try it and hope that it works. Okay. So if I want to just throw 100,000 of these, so basically I have the name of the program, the configuration file I want to use, the output file. So this will be the thrown 4 vectors in the AmpTools format that I'll talk about a little bit later. And then -HD will put out an HDDM file. So the HDDM file is in a format that can be read in by our simulation software and then used to do the simulation. -N is just the number of events we want to simulate, and -R is the run number that you want to set. Because when we do the simulation, we're going to start reading things in from the CCDB, which is our database that contains all of our conditions. And so if setting the run number will declare which run it tries to go and grab these things from. So to be consistent with this Sim1 data set that we already started, we'll set the run number to be 10,000. So if I run this, you'll see that it starts to do some initialization for the for the coherent Bremsstrahlung because it's being done in two places. One is the one where it's trying to get the intensity as a function of the energy right, and then the other one where it's trying to get the polarization as a function of energy. So it's going to call this 3 times to initialize these tables, and then it will start throwing events. Okay, so now happily it's going along its way. And you'll find very soon that this is definitely the fastest part of this exercise. Okay, so we generated 100,000 events just that quickly. So in the directory now, there's this, there's the files that we were looking for. This is probably way too low and way too small for anyone to see. Okay, so there's the AmpTools format thrown, which is the root file in the AmpTools format. There's this where's the other stuff? So there's this Gen3 Pi diagnostic that's just some diagnostic histograms that are in that sim omega code I showed you earlier. So this will be, I'll show you some examples from this shortly. And then there's the HDDM format file that we'll use to actually go in. Since we generated 100,000 files, it may be useful for you, if you've done this, to look at this 3Pi diagnostics histogram file. I will show you some of the output, though, in here. So basically, this is the output of running this code. So basically, what we have is all signal. I mean, you can see everything's sitting here on the omega mass. And we've thrown this, so we have you can see basically the shape of the number of photons. So we're peaked at 9 GeV here, and you can see, so here everything is sort of, the amount of this shape is uniform in energy, but that's just the way that it works out in that W formula. But you can see that here, where we're modeling the phi dependence, that it actually does depend on the energy. So at lower energies, things are flatter because there's less photon polarization, whereas right near the peak, you start to see this variation, the oscillation that you'd expect based on what we input. So in cosine theta versus, this is not really, don't read this, it's just cosine theta and then the number of entries. This is sort of the 2D plot, and then these are just the two projections. So this is the phi versus cosine theta, and this is just integrated out to be just phi, and this is just cosine theta. So this is just what we put in. So this is the signal that this is the million events actually. It's more than actually. Oh no, this is actually 100,000 events. So I basically did this for 1 million events, and you just fill in the statistics somewhat more. So that's one of the things that needs to go in. So now we have the thrown 4 vectors for our signal sample. Then we need to create a sample that's flat in the angles. So here, everything is basically the same here, except we've dropped the amplitude that would correspond to the angular distributions. So now we won't model any angular distributions. So you don't need to do this necessarily now. Here's just the results of what you get. So you can see that now that we haven't modeled the angular distributions, everything is flat in cosine theta and psi. You still have the same beam shape, so there's still the same number of photons there, but you don't have any modulation there in phi. The Dowitz plot is basically flat. There's some stuff on the outside that basically comes from the tails of the bright Wigner, but most of the region in the peak there is fairly flat. Okay, so that's basically our 2 input samples. You have one that has to be flat in whatever physics you're trying to study just to get the acceptances, and then you have the other that actually looks like the signal you're trying to extract. So before we head on, you might have had time to look at that root file. But if you try to run the next steps on 100,000 events, we'll be here forever.
Define how forever. How long would it take you to do that?
Well, okay. So for 10 files, I would run it about, so for 10,000 events took about 8 hours.
Okay.
80 hours or so.
This is the Jan stuff?
This is the Geon step, yeah.
Can you do it with 10 files that were how big?
10,000 events each. No, they were each 8 hours.
Oh, each 8 hours.
So you run them in parallel, and then yeah, sure, it takes 8 hours, but there is EM background, so that always eats.
Yeah. The slow part is the simulation view. That's.
Okay, so I'll just let this go in the background and make our 25 event sample. Okay, so here's something that we really haven't talked about until now. So we've given you all these simulated samples, but we haven't said how do you make the simulation once you have some 4 vectors that you want to pretend like went through the detector. So we need to swim them through the detector to simulate the response, and that's with a program called HDGeon that under the hood is Geon 3. Eventually that will move to Geon 4, but everyone in the collaboration knows how that goes. So basically there's this one configuration file for HDGeon called control.in, or at least that's the file that HDGeon will try to load by default. There are a lot of settings in this file, so it's the kind of thing that it's pretty well documented. If you get one of these versions that people are using, every single thing is sort of well documented. I'll take a quick look at that just so that you can see that you're not going to be completely in the dark when you run into these things. So at least Richard is thorough, and you can see sort of that we are going to use this particular input file that we have decided to name. There's this beam card that's going to use that same coherent Bremsstrahlung generator, but this is going to just be used for our EM background so that it knows sort of what sort of energies, photons it should be simulating. The output file, so the output file comes in this other HDDM format. So HDDM is sort of the input to Geon, but HDDM with some different information is the output of Geon. So there's all these different cards. The other ones that may be important that get changed often are things like this background rate, where it's basically how we describe electromagnetic background in the events, and this is described in this thing here. So this control in file is the same that is used for the Sim1 data that you've been looking at already. Okay. Back to this. All right, so now we're going to take our 25 events and go through the simulation. Yeah.
Yeah, just so that export command, that should be Janet context, right?
Yeah. Sorry. Typo. I believe it's the right thing in the other one, but okay. So, okay, depending if you're using the farm, i.e. Tegan, you should use setenv and not export, but all right. I will fix that. Oh, it is already set? Then maybe that's why it worked in the first place. Okay, so we can skip that step, and let's just go right ahead and run HDGeon. Okay, so now it's starting by contacting the database and initializing a bunch of items here, and you'll see that really at the end of this, when it starts running, this is what's going to eat up your time, is running HDGeon. And so thankfully we switched to be 25 events. In the meantime, is there anything else I can talk about? Okay, so now there's the next step is going to be, so now we've used HDGeon. This is now propagated all of these tracks through the detector and measured their energy deposits there and the timing of it. And now, but it's the exact information. What you really need to do now is smear this all out so that it looks like how your detector sees it. So there's another program that runs after HDGeon on the output file of HDGeon called MC-Smear, which is going to try to simulate all of the way that the detector sees this. So as we see, we've made it through 10 events. We're slowly gaining. So after we run MC-Smear, we finally will have something that looks like the data that we actually measure in the experiment. And the fun thing is that we can then just look at this. So and whenever this is done, we will I can show you the viewer quickly, and you can see kind of how these events look in the detector in a minute. Okay, so actually, since you're all sitting there, if you're not paying attention, you can catch up quickly to this point. So the README file here is actually an executable. So if you just run the README, you'll get up to this point. So it will bring you all the way to the point that you're displaying the events. And it's worth doing because the viewer is kind of fun to play around with, and you can see all sort of features of the data just by looking at it. Okay, so we've finally made it through this step. All right. Now the smearing itself is not all that intense. It takes a little while to get these Janner processes running because it needs to get a lot of things out of the databases. Okay, but once it actually started processing, it's done instantly. Okay, so now, like I said, we can look at some of these just to give you a feeling for how they look in the detector. Okay, so now you can see all the individual events here. So what you see is sort of the XZ and YZ views on the left-hand side, and then looking, this would be upstream in the CDC. So you can see the CDC hits here. These are the stereo straws, which you can toggle over here. You can turn off and on the hits from the CDC. These blue dots are the FDC pseudo hits, so it's after you've combined the cathode and the cathode strip and the wire information into one hit, and so you can turn those on and off. You can also see the energy deposits in the calorimeters. So here's some big energy deposit in the FCal. The fits are here, so you can turn them on with the decharge track here, and the neutral particles, you can also see where we've reconstructed neutrals. And you can see that even in these events that we've only thrown so many things, we have all these extra reconstructed particles, and this is where this idea of getting all the combinations and really having to search for the right combination comes in. So hitting the next button, you can scroll event by event through these, and you can see sort of what these signal events look like in the Monte Carlo. So this is what you're going to step through. Your code is going to go event by event and look at this and try to extract the signal. So there's tons of fun to be had just staring at things here, but I'll leave you to that. Okay. So now, like I said, we have finally something that looks like the data that would come off of the detector. Well, hopefully looks like. In reality, as Sean told us, it doesn't really look like it yet, but for now, it's as good as we're going to get. So now we can do all this other stuff that we've already developed. So we first want to make the REST files and run this monitoring HISTS plugin. So now it's going to go through, and so REST is going to be just a format that has our reconstructed objects, and monitoring HIST is going to make all of these interesting monitoring histograms. For us at this point, since we only generated 25 events, these are going to be very boring, but I have already the full output for 1 million events saved, so we can look at them at the end. So this is basically how you would step through this. So now you have your REST files, and you would then run this Omega Ref plugin that we developed with Paul to do these loose cuts on the Omega, and output the trees for that pass our initial cuts out of Jana. The next one will be to run the deselector that we developed with Justin. I've put a copy into this session that has all of the answers in it, which is pretty much just uncommenting things. So, well, that's a shame. We're missing a file here. It's supposed to be a tree Omega. Okay, so now we've loaded the deselector library and the file that we want to run over. And then we just process it with our deselector. So you see the 25 events. This is all very fast. And so now you've sort of made it to the point that you've selected the events out of your signal samples. So we generated them, we reconstructed them, and then we put them through our analysis cuts. And then comes the question of, okay, so now we've done all of this stuff. Now what is left? So what does our flat sample look like after we fed it through all the detector acceptances? So remember that we generated this with just some exponential t distribution, but the t distribution gets shaped by the acceptance. There's nothing in low t, and there's even this little crease. And if you were to fit this distribution, you would not really get the same t distribution that you threw. It's slightly lower than 7.5. The other thing that's important to look at for the fit we're going to do, since it's really just in the angles, is that when we threw a flat distribution, you get back something that's nearly flat. So in phi, you're basically flat here. But there is some cosine theta dependence in the acceptance that comes from this, most likely comes from this gap between the CDC and the FDC, where you saw in the other plots where we were looking at the efficiencies, that there's sort of this gap where we're a little bit inefficient in the reconstruction there. So there's this hole in the efficiency here that slightly lowers our acceptance. As for the angles, you can see that now we don't have edge sharp of a peak here in the mass of the 3-pi system. It's now been smeared by the detector resolutions. The phi distribution still, if we think about the flat distribution and how that phi distribution came out, this should sort of reflect what we put in. But you can see that we're sort of flattened out in cosine theta here, and that's due to that little dip in the efficiency for the cosine theta.
So these are the angles that you defined in the Felicity frame?
Yeah, these are in the Felicity frame. Okay, so now you should understand what I was talking about on the first slide. So we have the correct physics signal and the file generated without the physics that we're studying, and then the result passing through. This way we can do our acceptance corrections to our signal sample and hopefully get out something that looks like what we put in. So what we have now is this output T tree that's in this format that contains a lot of unnecessary information for AMP tools, because AMP tools really only needs the 4 vectors there. So there's already a tool to convert the combinations that are passing these cuts into a form that's suitable for AMP tools. So there's this tree to AMP tools, where you basically define the file name of the output and the name of the tree. And it's basically done the conversion here. So what you get is you go from something that looks like this, where you have just sort of endless amounts of stuff in here that would be useful for cutting on any number of things, to something where you really just have the four vectors in the format that you need them. So you have what the energy is in the final state, and each of these is an array of all of these for the number of particles you had in your output event.
I mentioned one dangerous thing.
Yeah.
So those leaves like PX, PY, PZ, those are arrays. So you've got several particles in the final state, so that's an array. And in the AMP tools code, Mike's reading them in. But it's really important to make sure that the array is in the order that you're expecting it to be.
Yeah.
So if he generates it with one array, hopefully the output from all of this is the same order that you generated.
Yeah, there's an unspoken rule that omega only goes to pi plus, pi minus, pi 0. It doesn't go to pi 0, pi plus, pi minus, or pi minus, pi plus. It goes exactly in that order.
So the order that this program puts it in is the order that you listed things in their D reaction. So just when you generate, try to keep that in mind. Maybe in the future versions we'll have a way that you can rearrange it in case you got it wrong. But just right now, it's in the order that you've specified way at the beginning when you were in JANA.
Yeah, and like you saw in the configuration file, it's also important that because when you set the reaction and then what the particles were there, you set them in the order that you expect here at the end. So you have to be consistent in your numbering here for this to really work.
What happened to the combinations?
So now for every combination that's passed all of our cuts, it gets into this AMP tools tree.
As separate events?
As separate entries. So for each one, you have some set of four vectors that describes that particular thing that passed your cuts, right? So you have the four vectors for the proton and you have the 3 pions and the energy of the beam.
Right, so those were background that you weren't able to remove with your cuts. So the background's still present in your fit.
You have multiple, when it gets,
in
other words, suppose there's 2 protons. Mm-hmm. Those 2 protons get passed to the fitting team, to the fit function.
So say you have one event and there's 2 combos that pass your cuts, then yes, they both get passed into the fitting team.
Well, maybe you're going to talk about it, or what?
I'm not
What
going
do
to
you
talk about it. It would constitute part of your background, and
no matter what analysis you're doing, you're going to have some background. So your fit needs to take that into account.
Yeah.
Right. So what does the fit do? I mean, if it gets 2 protons in the...
It can't get 2 protons.
They're treated as separate events entirely in this tree now.
Oh, that's
we
what
come
I
back to the
asked.
point raised by Matt before. I mean, it's a general question how to treat this, because you need individual events, of course, for the partial wave analysis. And either you choose, like, using chi-square or something better, the best combination, or you artificially increase the statistics somehow.
Or you can cut away all events that have more than one.
If there are not too many.
Yeah.
I think it's all dangerous. But.
Well, having an efficiency that depends on your ability to predict the number of multiple combinations. Taking one per event.
I think it depends on your.
But is it, to implement it in the analysis step, is it easy to just, let's say, write a filter just keeping the best chi-square event?
Nope.
Okay. Good to know. I mean, you could. I don't know.
You could write code to do it yourself.
Yeah.
There's nothing that's
I
like
mean, this is what I meant.
It's
but
nothing
I think it's-
pre-coded.
I
But
mean, in the place in the deselector where we wrote out this new tree that was a clone of the previous one where you just had things that passed, you could put something in there that just put in, it only set the flag to keep that combo for the best chi-square. So you could write out this tree from the deselector which just kept the best chi-square.
Okay, there
combo.
will be possible to do
Yeah.
something.
yeah. There's nothing pre-built to do that, but it wouldn't be
It's
difficult.
no big deal to do so, let's say, that was the question.
Yeah. Okay, so this whole process that I just showed you, we've done that for 1 million events. So we've gone through 1 million events and we've produced these files. So now we want to go into performing a fit here. So this is the configuration file that we'll be using to perform the fit. Basically, once again, you define the reaction in a similar way to you did the input. What we're really interested in is this next part that people in the back can't read. So basically we have all these, you can name parameters in AMP tools. So we have this parameter that's each of these spin density matrix elements, some initial value. We want these to be bounded between -1 and 1, just arbitrary choice. Those aren't really the physical bounds for these. That's a whole different set of numbers. And then there are, like I said, we need these 3 files. You have some generated Monte Carlo, accepted Monte Carlo, and data. So here we've had, so there's this already pre-existing data reader. This is all stuff that's already been developed for GlueX, and then these are the names of the files that are going to go in. And these are all in that AMP tools format where you just have the 4 vectors. And so finally, we're just going to fit this one amplitude. That's the 3 pi angles, and then we pass each of these in, and just some in brackets. You put the name of each of these parameters, and then we'll just use fit-c with that configuration file. Let's see. So now what it's doing is it's going and it's using these same amplitudes that we use to generate things, but since we registered this as a parameter, it's going to go through and do a maximum likelihood fit, basically, of all these events that are left in our files. So it's performing integrals to get these things as probability distributions, and basically it's going to just perform this maximum likelihood fit. The way that this is coded currently with all of these parameters stuck in the same amplitude is not really ideal for the speed of this. So this is going to take a little while. It's going to probably take about 2 minutes for us to fit this one set. And so so basically, things to consider is that we haven't really touched on the background here. And like you saw in Justin's talk, there really isn't a lot under there. But what's going to happen if you do include something like the background is that it's going to tend to dilute out your signal, assuming that it's flat. So you'll basically sort of raise the baseline on all of these, and you'll sort of wash out the angular dependencies slightly. I'll talk about a few more caveats later, but maybe we can just go there. Well, or rather, I actually have the result. Okay. So once we've gone through this, we haven't accounted for any of the background in our events. So you can see that we have each of these where we've returned some value for it, and the error, the statistical error on that value. The 2 that we set are 9, where we set this to be 0.4. We get 0.37. It's a bit lower. And then also this other one where we set minus 0.2, you get minus 0.18, and the rest are basically consistent with 0. So you can see that there is some washing out of what we get here already, and that could be associated with these double combinations or something like that. This is something that I'm currently looking at. I really don't know the answer as to why you don't get exactly what you expect.
Those other parameters are not consistent with 0.
Sure, with the statistical errors, yeah. Everything's sort of, the exact leakage between values, I don't want you to read into this too much. I haven't debugged enough of this and looked at enough detail to say why these things are, it's not consistent within the errors, but I don't know why that is.
There's systematic uncertainties in our study that we haven't put in.
But at least there's some conservation of strength.
Yeah. I mean, you see the general trend of what you put in is what you get out. But.
Will it run faster if you make the bounds tighter?
I don't know. You could try. So it will run faster if you just fix some of these. So if you say that these other ones are 0 and you fix them, then it runs much faster because it has less parameters to optimize. Okay, what else do I have? So yeah, so some things to consider, like I was saying, we haven't really considered, we're not including any of the background from Sim 1 in this fit right now. Really, at the end of the day, you should do something more sophisticated with your background, whether it's some sideband subtraction, or you can even use Q-value weights. So if you wanted to really try to pin down removing the background from your sample.
So just a word about that, and then I don't know which version of AmpTools you have, but in the new version of AmpTools, there's a background keyword. You can supply a background file,
Okay.
and the file is supposed to, you supply a file that's supposed to be appropriately weighted to match the background in your signal. So sometimes this is done by having a really large sample, and then you just weight it down such that the sum of all the weights matches what you expect the background level to be in your signal. And then it compensates for that in the likelihood fit by subtracting.
Oh, okay. So that's nice. Something to play with. The version of AmpTools that's here is the latest, so
So it's probably here. You just so
yeah. Also, if you misselect the beam photon, you can dilute these angular distributions, because you can imagine you picked the wrong energy, and that means you've also picked the wrong polarization for that photon. So that sort of feeds into this amplitude for the 3 pi angles. You could have some angular dependence in your background, and you better watch out that you don't have polarization dependence also, and things like this when we start to combine these different para and perp samples. Obviously, in some real analysis, you'd want to bin this in EET, cosine theta. And really a big caveat is that in this fit method where you're just kind of fitting to the angles, you might get non-physical results. So it's not something like Curtis was describing, where you have this set of S waves that you fit and then project out all these spin density matrix elements. Here, it's just kind of doing some numerical optimization of the angular distributions based on your function, and whether or not that converges to something reasonable, it's questionable sometimes. In the simple cases where you have something like this, where only 2 of these are going to be non-zero, if we really have some T-channel Pomeron exchange or something, then it's probably not going to be non-physical very often. Okay, so I wasn't sure how long this would take. So I guess I used an hour of my hour and 20. So for exercises, is just play with the fit. So change these initial values, which parameters you fit, limits, see if it makes any difference. It's just have fun with this, because you have this data and you want to see like how the machinery is tweaking your value and whether it has any impact. You could also change the cut and see how and go through, change the cuts in these event selectors and see whether that changes the results. The rest files that were used for the million events are at this location. So you can, well actually they're being rest, sorry, I have to change that too. It's not in root trees. So you could use that, and you could really test going from these rest files, which is sort of what you'll get if you're doing a real analysis, is you'll probably have access to the rest files for some set of runs. And you could try going from that into some point that you actually can do some further analysis. So I've also included in this workshop session 5A, also a bad link, sim 1 million omega histograms. There's a root file of the background that should, so it's the file that Justin was talking about in his session, where he's removed the omega signal, and it should be a number of events that would correspond to our million generated omegas. So if you remove the omegas from the sim1 sample that's there, and you replace them with these, you should have the same sort of cross sections there. So you could look at, so one thing to look at right away, which would be a good thing, is just look and see if these from Pythia have some angular dependence, and you'll see, looking at these histograms, that yeah, there is some cosine theta dependence in this background that's modeled by Pythia, which should be, I mean, presumably basically flat, but I don't really know what's happening in Pythia. So there's also the AmpTools ready trees for this background in the AmpTools trees folder. So you can try and just add these into your other sample and see if they fit. You could try using this thing that Matt was talking about, where you might just put the background in and see how things change. It's just sort of, it's a toy model, so I encourage people to play around with it. Let's see. So, are there any questions? Great. Crystal clear. Now Vincent will talk to you and tell you about how wrong this is. Well, in a little while. I guess Justin's up next, but do you want to go, should we start right now, or do you want to?
Up to you, Justin.
take a 10-minute break and come back a little early for the next.
Yeah, people can play around for 10 minutes and then start the next talk.
Some space, which now if I go back to my ordinary operating system, that's basically stop the virtual box.
The memory?
Yeah.
Yes.
So I should be able to disable it.
Yeah.
So I had like 25 gigabytes and now it's showing 3.
Of memory?
Yeah.
Oh, disk space.
Disk space, yeah.
No.
You have to actually delete
They wash out because the fit rate makes them not orthogonal, right?
No,
Or the
word
efficiency makes them not
unpacked.
orthogonal.
That was a compressed thing.
Okay.
This is like really
sorry?
20 gig.
The way it's washed out. Am I understanding how you spectrally decompose things, or am I completely off base?
You have done your wiring.
So
Yes.
if the efficiency was flat, if you had a perfect detector,
Well, I mean, I had
then they wouldn't wash out. Is that true?
Hang on here. I removed all my photogalley.
Okay, so if I put my generated as my accepted and then use my generated as my data,
Yes. Yeah.
it's much closer to not washed out at all. Yeah, it's not washed out. It should be.
Right. But so the functions that we're fitting are no longer a orthogonal basis of what we're trying to fit, because we threw the accepted out.
So
Is
I
that
don't create.
true, or am I
don't create
completely off base with how
events
these parameters work?
for showers.
I mean, like
that
Curtis
do
was saying, now you ignore the
ways that I know
correlations
that they're
between
good
these spin density matrix elements
just
once you
by looking at
parameterize
the
it
tracks
this
and
way.
seeing if they're
But,
fine.
and that's valid as long
Tracking
as they're
finishes.
a basis of the function you're fitting,
Time-based tracking
but,
finishes.
or an orthogonal basis, really.
Great.
And they're an orthogonal basis as long as the acceptance is flat.
Then I
But once the
create four
acceptance isn't
vectors.
flat, they're not an
Four
orthogonal
vectors
basis
don't
anymore.
exist.
There
until
are
after time.
there are cases that if you have some non-trivial phi acceptance that you might adjust even your capability of measuring these things in this way. So you might be right that it is something like that.
Okay, I mean, I'm just trying to get an intuitive handle on this.
Saying the correction for the acceptance doesn't bring you back to having an orthogonal basis?
Yes, I'm pretty sure that's true. On some level, it has to be true, because you could, like, just, if your acceptance is 0
If I'm
over half
generating
your
it from
detector,
photon, okay, I say, okay, it's going at the speed
these
of
bits are
light.
no longer orthogonal bases of the reduced ranger.
Then,
At least that's
get the
true
point.
of Legendre
Points at the
polynomials.
center
If you
target,
like chop out the middle half of a Legendre polynomial and only fit here and here, they're no longer orthogonal bases of the thing.
something
The
else.
integral of, if you integrate over here and ignore the middle, they don't come to 0.
Shower.
So I'm assuming this spark of S waves works the same way, or this set of S waves that you're fitting over something else works the same way.
If it's a hadronic shower, yeah, they wouldn't be any.
It would be interesting to study.
I mean, I don't know how you fix it.
Yeah.
I don't know if you do fix it.
I'm saying there wouldn't be a 4-vector associated.
Mike has written this down before, so I think I know what you mean by the Q factor that you're weighting when you put it into the fit. And when you write that down, that Q factor is what makes the functions not have the properties you want them to have to make the fit work the way it's supposed to work. I think there's an angle, or many possibly, over which these functions can add to each other and where you can shift stuff around.
There's no Q factors here.
Here, sure.
So there's no background. There's an acceptance factor,
Okay, acceptance.
which is the base Monte Carlo.
Okay, the acceptance factor. Yeah.
Okay.
Sorry. I don't know this terribly
No,
well.
that's
So.
fine.